Necessary, so we should get started. I'm going to introduce our illustrious colleague, Ken Segal. Just a few things about him. He did his undergraduate at Liberal Arts School at Fairfield College, University.
2,800 students, just like Kobe.
And was a quarterback, right?
Back up.
And he after Fairfield, he went to Yale, where he got his PhD. Then he did a postdoc at MIT. And then all with the people that he's continuing to collaborate. And then he came to Colgate in 2003. Okay, 2003. And then he is actually he was hired responding to a request from the students who wanted somebody that would do some applied type of research. What he does is quite fundamental as well as applied. And then that's what led us to hire Ken. And then he has been doing some unbelievably cool research. He's been collaborating with colleagues at Yale and MIT who are involved in probably at the leading edge of implementing a quantum computer. And then Ken is actually doing his thing, is having his own efforts here to build a quantum computer, but of a different kind. One where the individual parts behave more like our brain as opposed to a standard computer. So, and today he's going to tell us all about supercomputers and the future of computers. So, without any delay, let's welcome Ken.
Thanks, Kiko. And happy to be here today. Happy to see so many people who made it all the way over to Lathrop. And I'll talk to you today about the sort of lead up to my research. This would be like the talk I would give that would be followed by my research talk. I'm going to leave my research to be described by my 4 research students at the 410 Symposium, which is coming up in a few weeks. So I don't want to steal their thunder, but I kind of want to set them up a little bit. And we do that by talking about something called Moore's Law. I'm always really, really surprised at how many people don't know about Moore's Law and the kind of impact that it's had on our world. And so it's really worth taking an hour to think about it. What is it? It's really a combination of engineering and economics that have led to more and more powerful computers over the last 40 years. And the important thing to note is that it's ending. After years and years of people saying, no, don't worry about it, it's going to be fine, it's really ending. And we'll talk about why that is. And then the question is, what is next for computers? What are the computers of tomorrow going to look like? And the answer is, we really don't know. And that hasn't happened for 40 years, and some people are really scared by that, and other people are really excited. And hopefully you and the audience are in the camp of being really excited, because there are some really, really good research opportunities to be a part of designing tomorrow's computers. And there's a very good chance that some kind of computer in the next 10 to 20 years is going to be made from superconductors. And that makes me very happy, because that's what I've been studying for the last 20 plus years. And so we'll talk about that, where superconductors might come in. And you might notice there are some things in the front of the room here that we can have some fun with today. So very informal, please feel free to interrupt me at any time, and we're happy to have a discussion. I actually don't have that many slides to go through. All right, so building a computer. We break open a computer, what do we see? So maybe you've even made your own computer. You can do this. You can order the parts on the internet and put the put the computer together yourself. You've got to wear a grounding strap, but you have some different parts here. And the main part is the processor. And if you look closely at the processor, you'll see kind of some background stuff that's kind of highlighting one main, what we call a chip. It's called the central processing unit. You see lots of wires coming into that chip. And if you took that chip and broke it open and looked under a microscope, you would be absolutely amazed that you see this incredible network of wires. It almost looks like the overhead of a city, and you see avenues and streets and buildings, things like that. And if you continue to zoom in even further, you would see some really amazing structures that are well defined on the nanometer scale. Okay. And in particular, the things that you're going to see are called transistors. Probably heard of transistors before. But transistors are amazing. They're really like the Lego blocks of computer circuits. And it's really actually quite a good analogy because, as with Lego blocks, you have different colors and different shapes, and you can put different kinds of Legos together to make different things. And that is exactly true with transistors. You can put transistors together to make oscillating circuits, to make memory circuits, to make gates that process ones and zeros. You can make circuits that drive speakers that emit power. And so it's really, really the right analogy here. Okay, so if you want to build a computer is essentially a very large circuit. The question is, how many Lego blocks do you have? Okay, so if we want to build something for Emmett over here, we could take 50 Legos and we might be able to build something. A little house for him, but it might be better if we had 500,000 Legos, and then we can build him a Death Star. Okay, and so that's really the analogy here. The more transistors we have, the more that we can fit on a computer. Now there's one piece that's missing here, and that is that, of course, this thing is a lot bigger than this. Okay, and so what's going on with computers really haven't changed their size in like 40 years. If you go back to the first personal computers, they're about the same size as the computers today. So if we're putting more and more and more transistors on there, they must be getting smaller. Okay. And so imagine taking millions and millions and even billions of Legos, but now each Lego has gotten a little bit smaller. You can put them together and you can really, really build quite amazing things. Okay, so let's go back in history. So this is the first transistor here on the left. It's about this big. Nobody knew what the heck they were talking about. There were 3 places where you could put in current. Actually, sorry, it's 1, 2, and 3. And they found that the current between 2 of them depended on the current between another 2. And you'd say, well, what good does that do? And it turns out it does a lot of good. It allows you to control the current through the circuit, and if you put lots of them together, you can really achieve some amazing circuits. And so that was 1947. In 1959, Jack Kilby started putting circuits together on a chip. So these are actually several transistors together. And very importantly, in a 2D plane, so you can start to see what's going to happen is that we can start to put more and more of these together, connect them with wires. Of course, here he just had macroscopic wires, but eventually they figured out how to make them on silicon chips and to make the wires out of metal and to be able to pattern the metal into these very, very, very complex circuits. Okay, and so we start to see, as time goes on, the circuits start to get more and more and more complicated, start to have more and more wires and more transistors. As time goes on, we start to make them smaller, cheaper, like that. Okay, and here's the main plot. This is Moore's Law. So Gordon Moore was the CEO of Intel, and he started to notice a pattern. He started to notice that the number of transistors on an integrated circuit was roughly doubling every other year. So first we had like 50, and then we had 100, and then we had 200, and then we had 400, and then we had 800. And of course, if you plot that on a logarithmic scale, you get a straight line. Okay, so here's the year on the bottom. Here's the number of transistors in chip, and this top number here is 50 billion. Okay, so that first transistor, which you could see with your eye, and we will be teaching 336 this spring, and you will actually see one transistor, and for those of you who take that class, you'll see how hard it is to just get one transistor to work and understand and do what you think it does. And think that today's computers and smartphones have chips that have 10 billion transistors on them. And they all work, and they're all working together in a way that's really transformed our world. Because of this growth, there have been a lot of really, really life-changing advances that have happened because of this. Okay, so in the early 1980s, we had the first personal computers. As you were old enough, you might remember the Apple IIe, Commodore 64. In the early 1990s, we had the internet. 1995 is roughly when the internet really started to pick up. And of course, in the early 2000s, we, for whatever reason, decided to put circuits in our phones and started taking pictures and being able to know where we are. And then finally, today, we have Fortnite.
Biggest laugh of the whole.
So, how did this happen? How were we able to do this? Okay, basically at every point on this curve there was a problem, there was an engineering problem that was solved. How do you make things that small? How do you connect everything? How do you fit everything? Do transistors even work when you make them smaller? What about edges? How do you test everything? How do you know all these transistors are working? And of course they're all electrical circuits, they all dissipate power, so how do you get all that heat out? And so there were a lot of advances that were made over this 40 years. Mention of called complementary metal oxide semiconductor transistors. Lithography is the general term for how you make these circuits. I'm not going to go into the details of that, but basically it's a photographic technique that allows you to sort of print these really, really small wires. Integration into the third dimension happened about 10 or 15 years ago. Much, much, much more. Okay. Now, what's driving this? Why did this seem to happen with regularity? My best example is to think about a treadmill. Okay, so what was happening is that people started to notice this pattern. People who wrote software said, hey, the hardware is getting better. We got a 2-year software project. Let's write the software for the hardware that's going to be available instead of the hardware that's available today. Because the hardware that's going to be available is going to be better than the hardware that's today. And so then the hardware people are starting to think, oh, geez, we better be able to figure out how to make something that works like this, because otherwise our products are not going to sell. And they're going to we're going to get out-competed by the people who do stay on this curve. And so it was almost a self-fulfilling prophecy that people had to figure out how to solve these engineering problems. They had to figure out how to stay on this curve, otherwise they went out of business. And lots and lots and lots and lots of computer companies went out of business. So there was a economic incentive to keep solving these problems with huge payoffs, of course. As we know, some of these technology companies are the biggest and most valuable companies in the world. And that translated into us moving further and further up this curve. Now, there's something really, really important to know. And that is that fundamentally, if we look at how computers work today, they're the same as they were 40 years ago. We're taking basically the same circuits that we had before, and we're just shrinking them and just repeating them. Okay? So the computer industry, in some ways, hasn't been forced to innovate in terms of how we do computing. The computers still have memory, they have processors, they have an architecture that was first first worked out by von Neumann. They're called von Neumann machines. They're based a lot on some of the work by Alan Turing. And they haven't changed. They've just been taking the same computer, making it smaller, and then you can put twice as many on there. Okay, so with more chips, with more processing, your computers can do more. Okay. So, how small have they been getting? All right, well, this is the same plot, but now it goes down because this is basically the size of each transistor. Okay, again, roughly the same time period. And you can see that we've been going down at a really steady rate. Okay. The right scale on here is nanometers, and I want you to notice that the transistors that are being made today in the last few years are on the order of 10 nanometers. How small is 10 nanometers? Just give you some perspective. A human hair, which students at 131 just measured a few weeks ago in the interference experiment, is about 100 microns. A grain of sand or clay is about 1 to 50 microns. The wavelength of visible light is somewhere on the order of half a micron, a couple hundred nanometers, a few hundred nanometers. An influenza virus is 100 nanometers. And the line width of circuits from a year or two ago was 10 nanometers. 10 times smaller than a virus, getting close to the width of a DNA molecule. And you can see a hydrogen atom is really not very far behind. These circuits are now hundreds of atoms across. Hundreds to thousands. Think about the kind of engineering that's going on that scale. Okay, so you got to have some fun with this. In 2003, the number of transistors shipped was 100 times the number of ants in the world. The price of a transistor is now much less than one printed newspaper character. So go look at the book you're reading, look at one character, think about how much that character cost, and you can buy several transistors for that price. because we're making so many of them, sort of de facto, they're cheaper, right? And that's really important. That's coming up. Time and tolerance of today's chip-making machines is less than 1/1000th of an inch, equivalent to driving straight for 400 miles and deviating less than an inch. And here's my favorite one. In 1978, a commercial flight from New York to Paris cost $900 and took 7 hours. If the economics of Moore's law were applied to that flight, it would now cost less than 1 penny and take about 1 second. So this is arguably the most powerful force that's been going on in the last 2 or 3 generations. It's really transforming our world. But it's over. Okay, so here's the same data that I showed. This is from The Economist, okay? And remember, we talked about economics. Economics is really the reason. And I just want to tell you, as a physicist, working on circuits that are similar to this for many years, it was always fun to talk to the silicon people, because you would show them what you were doing, and they would say, oh yeah, that's cute. So, well, we're not going to do that. Say, but you could make a new computer, do something different with this. They say, yeah, but we're not going to do that. And for many years, physicists were saying, you're not going to be able to keep doing this. You're going to run into problems. You're going to have short channel effects. You're going to have quantum tunneling from the source to the drain. All these, harbingers of doom. The engineers won at every turn. Physicists said, you can't keep doing this. Engineers said, don't worry about it. We'll solve it. And they did. And there is no reason why, even as small as they're getting, there is no reason why they can't keep doing it. Okay. But why was this curve like it in the first place? It was this way because of economics, because there's an incentive to keep solving these problems because you're going to make money. Okay. Notice this curve in the upper right. Transistors bought per dollar, millions, by the way, this is millions of transistors. Okay, so in 2002, you could buy a few million transistors for $1. In 2010, you could buy 8 million. In 2010, you could buy 15 million. In 2012, you could buy 20 million transistors. what's happening, as we're making them, we're finding more efficient ways to make them, and the cost is going down. But look what happened. Somewhere in the last 4 or 5 years, that curve has leveled off and turned around. Okay? So the price per transistor is now going up. The number of transistors that you can buy for $1 is going down. Okay, and that's what the problem is, right? So what's happening is that the engineers continue to win, they continue to solve the problems, but it's now getting so expensive to solve those problems that you're not getting your investment back. Okay, so by Intel's own admission, the same engineers who rebuffed me in the 90s are now saying, we can't do this anymore. We can't keep solving these problems, it's too expensive. Okay, and so there have been a lot of articles, I didn't print out any headlines, but you can go search on the end of Moore's Law, and you will see there are a lot of articles about how in the last 4 to 5 years, the semiconductor industry has basically come out and said, we're not going to do this anymore, we need to find other ways forward. Okay, let me tell you about a related problem. And that is that, as you know, a lot of computing happens in the cloud these days. What is the cloud? The cloud is essentially a very large computer, or a supercomputer, right? And supercomputers have been kind of on their own Moore's Law. Here is the largest supercomputer in the world as a function of time. And now we are, instead of putting the number of transistors here, I'm putting the number of floating point operations per second that computer is capable of doing. So this is essentially processing speed. Now, why do these computers work this well? Because what you do is you take lots and lots and lots and lots of individual Pentium chips, and you put them in a big rack, and then you have really good programmers who are really good at taking computing jobs, splitting them into tiny bits. You send each bit to one processor, you recombine the bits, and then it's like, if you have 10 processors, it's almost like you have one processor running 10 times as fast. You pay a little bit of overhead, but it's a very effective way, called parallel computing, very effective way of solving problems. Okay, so for a while they're doing this, and things are great, but there's a problem, and that is that you have to plug all these chips into the wall. Okay? So you might have a computer that has 1,000 or 1,000,000 cores, that's like 1,000,000 Pentium chips there, but they all need a certain amount of watts to run. Okay? And so you can plot it on a log scale and it's fine, but when you're talking about power, what does that look like on a linear scale? It looks like that. So this is the power demand of these supercomputers, okay? And you can see we are now into the megawatt range. Beth, how much is 50 megawatts?
Well, like a big nuclear power plant is a gigawatt. 100 megawatts is a pretty big electrical power plant.
Pretty big electrical power plant. How much is a city, small city?
Well, it's probably around there. One electrical
Yeah, I think the power of Syracuse is somewhere on the order of 50 or 60 megawatts.
Wait, do they have these built?
Do they have these built? We're somewhere around here. So these were built. These are going to get built. How much further do you think we're going to go with this? Not much further. Okay, and so this is another alarm bell that's been going off, is that energy is becoming a big problem. Here is the Facebook data center that was built 4 years ago. You notice anything about it? It's big. You notice the snow in the background? This is the Arctic Circle.
What?
You know why they put it up here?
Free cooling.
Free cooling, cheap energy from hydropower. Okay? So this is a problem as well. Okay, so where are we going? It's tough to make predictions, especially about the future. I kind of love Yogi. He's the best. Okay, so there are a lot of horses that you might bet on if you're looking ahead to the next 5 to 10, 20 years of computing. One of them is quantum computing. I'll talk about that in a second. One of them is to try to make cloud computing that it's more efficient. Okay, and there are a lot of people doing research in this direction. Turns out these silicon circuits that have lots of transistors are not super efficient. They were never really worried about power because, your computer doesn't actually draw that much energy from the wall, right? But these supercomputers do. So there's a whole bunch of people trying to go back and figure out how to make more efficient circuits starting at ground zero. So the area that I'm working on is something called neuromorphic computing. We don't even start with ones and zeros anymore. We go back and we compute with spikes, the way that your neurons communicate with each other. So that's another way to go back and sort of reinvent computing, quantum computing as well. Okay. So like I said, we've been living on the same circuits for so long that a lot of ideas in the last 40 years have been sort of passed by. And some of these ideas have been around for a very long time. Neuromorphic computing was, Carver Mead basically invented neuromorphic computing in the 80s. Richard Feynman suggested quantum computing in a lecture in 1981. The energy efficient circuits that they're talking about, most of them were done with Landauer in the 60s and the 70s. Okay. So these ideas have been around, they've just been passed by. The silicon people said, yeah, that's cute, but we're not going to do that. Right? Okay, but these all involved superconductors. And so that's my research, and that's what I wanted to talk about for the remainder of the talk. So let me just do one slide on each of these. So you may have heard, and this is literally a week or two old, this is the cover of Nature from late in October, Quantum Supremacy. This is a group headed by, or funded by Google, that is headed by John Martinez, who is a former professor from Santa Barbara and the National Institute of Standards and Technology. Little piece of trivia. John Martinez once offered me a job, and I turned it down. I say, wow, Professor Segal is really smart, or he's really stupid. Because he is the main architect behind this quantum supremacy. So this is the idea, is that you have bits that are not 0 or 1. They're bits that are in a quantum superposition of 0 and 1. And by using these probabilities, you can compute in a very, very different and novel way. Some problems, this doesn't really help you, but there are some problems where it really does. Okay, and so there's a big effort going on to try to make this quantum computing work in a way that would actually be beneficial and solve some important problems, and perhaps somebody could make a product out of it. Okay, the big news came because the Google group actually made a circuit that they were able to verify its operation with supercomputer, first with laptops, then with multi-cloud, multi-core computers, and eventually with a supercomputer. 5 hours on a supercomputer, they were able to get the same result classically with a normal computer that they did with their quantum computer. Then they turned up the gas on the quantum computer, and down here they're able to compute an answer that would take 10,000 years on the world's biggest supercomputer to calculate. Okay, there's a lot of details here, obviously, that I'm passing over, but this is called quantum supremacy. They've been predicting that this was going to happen for a while, and it did happen about 2 weeks ago, at least reported. And so the idea is that now a quantum computer can do something a classical computer can't. Now this something,
What time?
10,000 years. This took like 20 minutes or something. 200 seconds. So that's really exciting. Okay, we're talking about supercomputers. So my field has really been energized by the possibility of a superconducting supercomputer. So here is a slide from, so IARPA stands for the intelligence, I stands for intelligence, R stands for research, I forget what the rest of it stands for, but basically they've been funding a very large program to try to make a normal computer, ones and zeros, but make it out of superconductors. And there are a lot of reasons why that would give you a more energy efficient computer. Okay, and so here is a superconducting, this is an extrapolation, an idea here, but potentially you could have a cryostat which holds the superconducting chip, and this chip, the chips in this cryostat would be able to do what the biggest supercomputer in the world right now, which is Titan, could do in this same amount of area with much, 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 much less power. Okay. Now we are a long way from there. If you think about transistors, remember I said there are 10 billion transistors on today's computers. The number of what are called Josephson junctions, which are the fundamental elements of superconducting computers, they've only been able to put up close to 1 million. Okay, so 1 million, 10 billion, long way to go. And like we said, the reason why a lot of those problems were solved was because of economics. And right now, there isn't the economic driver to get this thing to market. It's really government that's supporting this. So we don't know if we're going to get there, but there's a lot of incentive to possibly do this. Okay, and then finally, neuromorphic computing. So some of you may have heard I recently was awarded a grant from Microsoft to do this kind of work based on some earlier results that we had. A lot of this is just people looking for horses to bet on, and our result was interesting to some people, so they said, why don't you try to do the next experiment? They were very nice about it. They said, why don't you just do what you were going to do anyway? So that's really exciting. So here's me in the lab working on my fridge that was just set up for this picture that's not actually doing anything. But I really want to not talk too much about this because less than 1 month away we have the 410 Symposium, and my 4 students, Ryan, Stretchko, Sharon Jeev, and Sandesh, are all going to be talking about things related to this. So please come to that in early December. Okay, but let's talk about superconductors and why they are playing a major role in this energy-efficient computing, this quantum computing, and also this neuromorphic computing. Okay, so what is special about superconductors? So you may have heard of superconductors. There were 2 experimental observations about superconductors when they were first discovered. The first is the famous one. They conduct electricity with 0 energy loss. They have 0 resistance. Okay, and it's not just like really small, close to 0. It's really 0. It's 0 in a way that nobody has ever been able to measure any resistance to any amount of decimal points that their equipment can resolve, and people have waited, I think it's like 10 or 15 years. You put a current in a circulating loop, and you try to measure the decay of that current, and that current hasn't decayed to the resolution of your meter in 15 years. So, it's pretty incredible. Less known is that they're also what are called perfect dimagnetism. They perfectly repel any magnetic fields. Okay, if you go inside of a superconductor, even if you've got a big bar magnet sitting on the outside, inside the superconductor you'll find that the magnetic field is 0. Okay, and that has also important consequences and maybe even some technological applications. Okay, so how did this discovery happen? Okay, so in the late 1800s, early 1900s, people were studying electrical resistance. They were studying electricity in general, and there was a big debate about what would happen to the resistance of metals as they got colder and colder. What they were finding is that the resistance was getting smaller. It was going down, it was going down, it was going down, and there were essentially 2 camps. One group that said, okay, it's going to keep going small, but then at some point it's going to level out. And there was another camp that said, actually, no, what's going to happen is it's going to slowly go to 0. And at t equals 0, the resistance has to be truly 0. Okay. By the way, t equals 0 here, we mean absolute 0. And the answer is the first camp won. There was actually a third group that thought that might go to infinity, but that group was small and was way wrong. So the answer is that for most metals, the resistance levels off. Okay, so here it is leveling off. For most metals, it just goes off. But Onus in Leiden in the Netherlands was the first one to liquefy helium, and he was the first one to go really, really, really cold, close to absolute zero. And so he started measuring this leveling off, and he was like, all right, looks like it levels off. And then he put mercury into his apparatus, and mercury's leveling off, and all of a sudden, poof, zero. And he's like, what? What just happened? Power outage? What's going on? So he did it again, and boop, zero, dropped to zero again, and somewhere around, is it 5 Kelvin? 5.2 Kelvin, I think. Mercury loses all electrical resistance, and so he didn't know it, but he had discovered superconductivity. And there are many superconducting metals. Some of them are very common: aluminum, niobium. Niobium is the one I use in my lab. Tin, mercury, lead. So pretty common metals. Lead goes superconducting at like 9 Kelvin, niobium at like 9.2. These are the two highest in terms of the elemental superconductors. Okay. Now, helium liquefies at 4 Kelvin. The next cryogenic fluid is something like liquid oxygen, which is in the 20 or 30 Kelvin. Okay, so it wasn't until you liquefied helium that you could actually see this. Okay, so this, for a while, was just a very obscure laboratory phenomenon. Okay, now let's talk a little bit about. Well, actually, let's do the. Why don't we do the first demo here? So let's show you that electrical resistance depends on temperature. We have a little liquid nitrogen here. So what I'm going to do is turn on this light bulb.
The red clip.
The red. That is a red clip.
Oh yeah. Yep. Okay.
It just has a black.
Yeah.
Okay. All right. So we have a battery that's in series with one light bulb. Okay. And you see the second light bulb is off because I haven't connected it yet.
Correct.
And go to the right.
Yeah.
Okay. So if I go to the right, I put the two light bulbs in parallel, and you can see that both light bulbs light up. All right. Now what I'm going to do is I'm going to take this entire spool of wire. Okay. So I connected an electrical path that starts at one end of this and goes to the other end. So along the way, it has to go through all however many turns of this wire. Okay. And of course, when I do that, I'm going to lose a lot of current and voltage, and the second path is going to dim, and I think it's probably even going to look like it completely went out. It actually is on a little bit, but it's really hard to see. Okay? So the electrical resistance has effectively killed that. Okay. But what if I cool the wire? So there we go. So if you didn't believe resistance depends on temperature, there you go.
Copper wire, it hasn't.
Yeah, it's copper wire. It's not superconducting. I just wanted to flex our demo muscles here a little bit. So that's just to show you that. Now let's do another experiment, which you may have seen in electricity and magnetism class. So we have this idea of repelling magnetic fields. Okay, so here's a little ring, and this is a solenoid. And so I'm going to put this ring on here, and I'm going to turn on the electromagnet. Okay, some of you have seen this demo. What's going to happen?
Jump.
It's going to jump. Okay, and why does it jump? It jumps because when we turn on the magnet, we have a changing magnetic field through that loop. That changing magnetic field, because of Faraday's law, causes an electric field or a voltage. That voltage induces a current, which we typically call an eddy current. the eddy current always configures itself to create its own magnetic field that opposes the change in the magnetic flux that we've instituted by the electromagnet. So what happens is that we have, let's say if this is the north pole of the magnet, the eddy current is going to flow in a way to give me a north pole there, and we have two norths together, they're going to repel, right? And so the magnet jumps, of course, and we have to do our proper control experiment, right? Just to make sure I don't have a little spring in there. Let's make sure that when I do this, that nothing happens. Okay? So,
See the slit there. Make sure people know there's a slit.
can everybody see that there's a slit there? Okay, so this one doesn't have a continuous, so no current can flow around, so I can't get a magnet to there. Okay, so what happens if I drop this in liquid nitrogen? Can I get a prediction?
So it's going to expel the magnetic field.
It's not going to.
It's not going to go superconducting, but it's based on what happened there. What's going to happen to the electrical resistance in the wire?
Go down, so it's going to go higher.
So I'm going to have less resistance there, which means I'm going to have more eddy current. So what's going to be the result?
Go higher.
It's going to go higher. Right?
Don't pick it up.
Don't pick it up. Okay. Now, what's the thing about eddy currents? The thing about eddy currents is that once they start flowing, they start, of course, the wire is not zero resistance, so, or the ring, so those eddy currents start to develop a voltage. Voltage times the current is power, so we lose energy, and eventually those eddy currents die away. Okay, so we can get a current flowing through Faraday's law, but we can't keep it flowing. We can't do levitation here because the eddy current only responds to a change in field. Once that eddy current has ramped up to some value, if we would have to keep changing the magnetic field, so we'd have to keep ramping it up in order to continue to have this eddy current flow. Otherwise, it will just die out, and then we don't have this opposing magnetic field anymore. Okay, but what if it's superconducting? Then those eddy currents never die away. Right? Then the magnetic field that we induce in this never dies away, and so I always have a permanent repulsion. Okay, so this is hot off the press. Thanks to Hans for ordering and figuring this out. So this inside here is a room temperature, not a room temperature, a liquid nitrogen temperature superconductor. It's called yttrium barium copper oxide. It was discovered in the mid-80s, and it actually goes superconducting at 95 Kelvin as opposed to 10 Kelvin. Okay, so liquid nitrogen liquefies at 77 Kelvin, so we can get this thing superconducting by just dunking it in liquid nitrogen.
Can you show what it does without without cooling?
Oh yeah, good point. Thank you, Tom. Okay, so this is a track of magnets that goes around. These are, if you've ever seen them, these are the neodymium, right? They're rare earth magnets that are really strong. Okay, so right now this thing is not, it's actually not even magnetic. Okay, so it doesn't do anything.
Anti-ferromagnetic.
Anti-ferromagnetic?
Yeah.
Oh,
All the HPCs are anti-ferromagnetic.
yeah. Okay, so we're going to cool this guy down. So now the problem we were having is that this thing actually has a little space inside, and the liquid nitrogen was getting in there, and it was kind of unbalancing it.
Oh my God.
Yeah, thank you. While we're doing it, I might as well throw the big one in here. Okay. So now, whoa. See, this is what it was doing before. I have to get the light out of it. So I'll try this home.
Just stay over, please.
See, this is like, it's got some... We got to figure out this imbalance thing, how it's like, it was doing this yesterday, right?
Down more. Then it kind of sticks. Now it's just goes wild.
Yeah, now it's getting one. Let's try the bigger one. Okay, here's something cool, is that these are magnets, one north and one south. So not only does it float, if I do this right, you can actually turn this over.
It's the square one.
It's a square one?
Yeah, and really push it.
I should really be wearing gloves here, not. Okay, so let's push it down. Okay, so, see that? Yes. That's cool. See if we float.
And that's because it doesn't affect the inside. That's because of where that's from.
So what does the double circle one do?
Those are opposing.
So it's the same thing.
Yeah, and then it... I think that this is supposed to rotate around. This doesn't stick. It just...
Oh, it doesn't stick. Yeah. Okay. We can have a lot of fun with this. And we'll let people come up afterwards. We'll just put these in here and get them cold. So let's see. So I've just got a few minutes left. Let me just tell you a little bit about why superconductors conduct without dissipating any energy, why they have zero resistance. So the thing about superconductors or superelectrons is that normal electrons, when they're sort of pushed through a metal by an electric field, they will go a certain distance and then they will hit something. They could, for example, hit an impurity or a surface or a vacancy. They'll hit something and then they'll scatter in a different direction. Okay, and when they undergo this scattering, that's when the energy dissipation happens. Okay, so what's special about when they get really cold and become superconductors? So what happens, and this took a long time to figure out. So this discovery was in 1911. The theory of superconductivity didn't come until the mid-1950s, right? So this was like 40 years. And don't forget, during that time, we did some pretty important scientific advancements, right? We figured out all of quantum mechanics, relativity. We built a nuclear bomb. So, this was a hard problem, okay? And what they found, what they realized, is that when you get really, really, really cold, a completely counterintuitive thing happens. There's an attractive interaction that develops between two electrons. They pair up. Okay, and they pair up through a sort of mediated interaction that happens with the rest of the ions in the. So if you think about a metal, you have atoms, and some of the electrons are sort of able to move between the atoms, and so they're delocalized, right? And the atoms that are remaining are then positively charged, because if you take an electron away, you're going to have a positive charge. Okay, so you still have these strong electrostatic forces inside the material where you have these free negative electrons and you have these positive ions. It turns out that there's an interaction that can happen where one electron talks to these ions, and that causes another electron to be attracted to it. Okay, only happens at really, really, really low temperatures, because at high temperatures these atoms are vibrating so much that they actually completely kill that possibility. But once you sort of quiet them down and get it really, really cold, that attractive interaction can happen. Now, the really cool thing about these pairs is that they change their quantum mechanical nature. In quantum mechanics, there are two kinds of particles. There are fermions and there are bosons. Okay? The electrons that we know and love from chemistry that fill up all their energy levels and result in chemical bonding and atomic transitions and all the things that we learn about are fermions. They are not allowed to occupy the same quantum state. They all have to have different energy levels or different angular momentum or different spin in order for them to populate that atom, and in doing so, they typically go out to a larger and larger radius. Okay, what these new paired electrons, you got to think of this guy as like a new kind of electron, a super electron. They are now bosons. Okay, bosons are allowed to occupy the same quantum state. They could all be in the ground n equals 0 state with zero angular momentum, as for example. And if you get them cold enough, you can energetically coerce them to do that. Okay? And there's a very good analogy to what happens in the superconductor transition to what happens in cold atomic gases. And that's what's called a Bose-Einstein condensation. So you may have heard about this, taken thermodynamics, or I think we will talk about it in 131 toward the end. If you have atoms at really high temperatures, of course, they behave like little spheres and they bounce off each other and exchange energy momentum. But as we get them colder, their wave nature starts to appear, okay? And their wavelength depends inversely on temperature. So the colder we get, the longer their wavelength gets, the slower they move, and the closer they get to each other. Okay, and so at some point, there's a really stark transition that happens where all of these individual atoms in this gas condense into one state, which is called a Bose-Einstein condensation. Right. Now, when that happens, all of these particles quantum mechanically are entangled with each other, and they no longer exist as single electrons. Right? You just have one state, one big quantum state with a capital psi. Okay, and so it doesn't even make sense to talk about a blue and an orange and a red anymore. They are just one big combined wave function. Okay, that is essentially what's happening with the electrons in the Cooper pairs. They are condensing into now one single quantum state. There's no longer single electrons anymore. And you can push that whole quantum state around with an electric field and not dissipate any energy. It's really amazing. It's quantum mechanics on a macroscopic scale, and that's why the quantum computers that I showed you in the quantum supremacy experiment were made from superconductors. It's that quantum it's this quantum mechanics that is being used to create the qubits, the ones and zeros that are in superposition state. Now, I'm leaving out a lot of details, so there's plenty of questions that we could ask, and welcome them in a second. But that's basically what's going on in superconductors, and that's why superconductors are being used for quantum computers. All right, so I think I will stop there. We're about 10 minutes, and be happy to take any questions.
What stops more than 2 electrons forming a Cooper pair? Can you have like 4 electrons form a Cooper quadrupole or something?
I think you probably could, but it would just be exponentially more unlikely. It's even unlikely for two to form. There has to be the right situation. The interaction has to be right. I'm sure there could be some interaction that could pair more than 2 or 3 or 4, but we haven't seen that. Yeah.
So what about the pairing up of electrons like stops them from interacting with the rest of the material?
Well, what happens is that the energetics of that state, it becomes energetically favorable for those electrons to drop into this now macroscopic state. Okay, so in other words, the energy of this is lower than the energy of that. It's basically that. And so in order to, like, if you want to now push on this with an electric field, you say, why don't these guys scatter like those other electrons do? Well, these guys don't exist anymore. It's this now. The only way to scatter this thing is to disrupt the whole thing, and that takes a lot of energy. Individual scattering events don't have enough energy to break up that state.
I think one way to say it is they have to have equal and opposite momentum to be paired. And if one of them scatters, it no longer has equal and opposite momentum, so it's not paired. And if you don't have enough energy available to break
up those pairs,
it's just not allowed to scatter.
There's just no energetically favorable way for it to scatter. Now, if you heat it up, then...
It's like instead of like bouncing off, it just says whatever.
It's quantum.
It's quantum mechanics. But that's the right question. You should be disturbed by that. Yeah.
So does it not take that much energy to cool the fridges that cool?
Oh yeah, really good question. It does. So you have to pay an overhead in this refrigerator, but that was included in this cost. And so what's happening is that you pay this overhead to get these chips cold. But once you do that, then you can make the circuit bigger, and you don't have the same increase in cooling power. So in other words, once you've paid the overhead to get them cold, there is still a certain cost that you pay. But basically, we're living, in an area up here where the heat is so bad, we're just really, really inefficient, that you can, even accounting for this refrigerator, you can get circuits that can dissipate much, much, much less power. Yeah.
What type of material would people be looking to use for superconductors in computing? Would it be like aluminum or?
Yeah, right. So, good question. So So it's mostly the low temperature ones, so not the ones that I'm using here. The high temperature ones tend to be really brittle ceramic materials. They have, huge unit cells, and they don't engineer very well. You can't draw them into wires, you can't make metal films, you can't make junctions with them. There's a lot of technical problems with them. And it turns out that the cryogenic cooling technology has gotten really good. So to go down to 4 Kelvin, even under a Kelvin, is turning out to be not such a big deal.
They do it in hospitals.
They do in hospitals. That's correct. They go to, when you get in an MRI tube, you're in a 4K magnet, and the quantum supremacy experiment was done down at 50 millikelvin. So the cooling is not so much of a problem. The two materials that are being fought over are aluminum and niobium. Okay, so the qubits, the quantum supremacy experiment was made with aluminum junctions. The cloud computing experiments are being done with niobium. So this is 9 Kelvin, this is 1 Kelvin, so you need a different kind of fridge for each of those. But you need to be cold anyway in the qubits because temperature kind of destroys your quantum state, so that's why people are perfectly happy to use them. But yeah, surprisingly, it's nothing exotic. Well, actually, niobium's a little unusual. It's used to line nuclear reactors or something. It's not a particularly common setup, but aluminum's pretty common. Other question? Yeah, okay.
Are most companies trying to find one kind of superconductor to see if that, like one kind of computing, or are they trying to find all of them to see which one turns out first?
Yeah, so good. It's interesting to see what different companies are choosing to do. Google is certainly going. Well, Google, I would say, has big footprints in both neuromorphic and in quantum. IBM has good efforts in both. Microsoft tends to be primarily quantum, and Intel has been mostly neuromorphic. So different companies are sort of pitching different things. But a lot of this is happening with sort of startup and venture capital companies where they're like trying to, make a new company with, some investment from investors. And so a lot of people are going that route. I think we're at 12:30. So thanks.